their states, how do these evolve? When they are placed in a magnetic field. Now, what we've seen is that when you place a spin in a magnetic field, the Hamiltonian is very simple. It's just the magnetic moment in dot product, in scalar product with the magnetic field. That's called the Zeeman Hamiltonian. That's got a name after Zeeman. And the magnetic moment is just this object. Alright, it's proportional to the spin vector. Alright, and the spin vector we know is proportional to the Pauli matrices. Right? So we did the algebra and convinced ourselves that if we're talking about spin half, then it's just a two-component object, the state space. Call it psi plus and psi minus. Look at the time-dependent Schrodinger equation. It's quite simple. Why? Because the magnetic field, right, if it's, let's say, aligned along the z direction, then this guy is just going to pick up sigma z, alright, the z Pauli matrix, which is diagonal. And then you can see that psi plus's evolution is going to be dependent on psi plus, and psi minus's evolution is going to be dependent on psi minus, because sigma z had only diagonal entries. It had no off-diagonal entries. So therefore, these equations of motion are very simple. And the solutions to these equations of motion are extremely simple. They're just these phase factors coming from the Hamiltonian, right? They're just telling us how these states will evolve. Well, you might say, okay, nothing very enlightening, but we'll see something interesting that's going to come very soon. So first, let's take the simplest circumstance. Let's assume that, okay, so remember here that this a plus minus, these coefficients, these are the initial values of the wave functions at some time t equals to 0. Okay, because you're solving a time-dependent differential equation, you need some boundary conditions or initial conditions, call it whatever you will. Here, these are initial conditions. When at time t equals to 0, we have to set something. Magnetic field is along the z direction. Okay, we'll fix that. So let's look at the simplest case. Imagine that the spin was also aligned with the magnetic field at time t equals to 0. Magnetic field z direction, spin also z direction. What do you think will happen? Even before you see an answer, what do you think will happen? Nothing. There should potentially be nothing. No dynamics, no interesting dynamics, no precession should occur. Because the magnetic field would anyway have wanted to align the spin with itself. This guy was already aligned. So it doesn't really need to do anything. But could there be precession? Could this guy start wiggling a little bit, doing something weird? Your intuition should tell you probably not. But let's confirm this. Okay, so time t equals to 0, we've just got the up state, 1, 0. That's the initial configuration. Okay, so which means that the coefficient a plus is 1 and the coefficient a minus is 0. Right? So then, plugging this into the solutions for psi plus and psi minus, given here, okay, we see that psi plus as a function of time will just be 1 times this phase factor, and psi minus as a function of time will just be 0, because it's 0 multiplying that phase factor. So that means that will always stay 0. Okay? So that means psi as a function of t has this phase factor on top and 0 at the bottom. So let's write this phase factor in a slightly more convenient way. Let's define something we call the Larmor frequency, which is 2 times the magnetic Bohr magneton, mu b, times the magnetic field divided by h bar. Okay. This has got units of 1 by time. It's a frequency. Okay. So let's rewrite this as this e to the minus I omega t by 2. Alright? And there's a 0 down here. Okay. So now, given the simplistic nature of this state, I can just pull that phase factor out. The other term, the 0, doesn't care. So it's just that phase factor times the up state. So you can see that, amazingly enough, this time evolution is this thing that we loved and admired about stationary states in the time-independent Schrodinger equation. Just a trivial phase factor being added on. The state doesn't really change, okay? Doesn't do anything. much. Up stays up. What that means is that the probability as a function of time, which is that you take the overlap of this psi of t with up and take the mod square. Okay. That probability, because it's just 1, 0 with this phase factor and 0, and the phase factor is just can be taken out and it's just 1, 0 again, the phase doesn't matter because you're going to take the mod square. So it's just 1, 0 with 1, 0, right? Row with column. That's just unity. That's just unity. Which means the probability for that state to stay up is maintained throughout. It's never going to change from that. So therefore, there can be no spin precession. The spin precession would have meant that something has to rotate. Okay? So up will just stay up. Why? Because the magnetic field wants it to stay up. It was already up. It's going to stay up. Okay? There's no need for it to do anything. Okay, so this coincides with our classical intuition. But then our classical intuition tells us also that, if this spin was inclined a little bit, the magnetic field certainly wants it to align with it, but it can also precess. Okay? So that means the best precession should probably obtain if I put the spin right on the plane that is perpendicular to the magnetic field. So the magnetic field is along the z direction. Let me align the spin, let's say the x-axis. Okay? Or you could do it to the y-axis as well, it doesn't matter. Let's consider the case where the spin is aligned with the x-axis. Yes?
So you say if it points towards the direction, the spin. So what does the frequency that you said lambda means?
It's just the time evolution. It's just the time evolution phase factor. That will always come. But what we'll see here now, when we have the spin along the x direction, is that we will get some phase factors, but we will also see that the direction in which the spin is present will also change, because that's what must happen if you have spin precession. So classically, you would say that if I have the magnetic field along the x-axis and the magnetic field is along the z-axis, precession should make this guy go around. That should be the precession. Okay? And we'll see that indeed that is okay. So the way this works out is following. So the initial condition is this, that psi time t equals to 0 is, let's say, right. Okay, the right arrow. Okay, that's the spin aligned along the x direction. How did we write that? In the up-down basis, we wrote it as 1 by root 2, the normalization, times 1, 1. Okay, this guy. Okay, so that's this thing. So which means that a plus, that coefficient, is 1 by root 2. Okay, for both, a plus as well as a minus. Both these coefficients are 1 by root 2. That's this overall normalization. Good. So then we plug it back into this solution again. Okay. We know what a plus and a minus look like. Put it in there. And what you can see is that you have these coefficients sitting there, and then you have these two phase factors. Okay, so it's 1 by root 2, and then it's that e to the minus I omega t by 2 and e to the plus I omega t by 2. Unlike in the last case, where the second entry was 0, here both entries are non-zero. When both entries are non-zero, it's not so easy for you to just take a common phase factor out and pretend that whatever remains is exactly what you had before. That's not necessarily going to be the case. So let's see this. So what we'll do is, so we've defined this Larmor frequency just as before, okay, and we can rewrite this state. Now let's see what happens at different time points. So at time t equals to 0, this is what the state looks like, okay. So this is the very general state, and at time t equals to 0, it was just this 1 by root 2, 1, 1. Now let's see what happens at some later points in time. So we have a Larmor frequency, okay, which means that we have a time period associated with that. 2 pi by this Larmor frequency should be a natural time period, okay. But what is the meaning of this time period? What does it mean to have this time? We'll actually discover that. Okay. So let's take a full time period. That should be the first thing that you should ask yourself. If I have a natural frequency, then something should repeat after that, right? After that time period, which is corresponding to 2 pi by that frequency. So let's take that full time period. Okay, plug it in here, because you have a state, a very general state here. Okay, plug in this value. When you plug it in, you get a surprise. You see that you actually get 1 by root 2, 1, 1 again, but with a minus sign coming about, which is just this e to the I pi phase factor. Okay. So you again get back to the state, the spin pointing right, okay, but it's accrued a minus phase factor. Now it turns out that if you were to do a second round again, 2 periods, not 1, which means you take a time period 4 pi by omega, then again you will come back to the spin pointing up again, okay, but this minus sign will have disappeared. It will come back to plus, okay. So that's weird. So what we're saying is that, look, I started, let's say, with this, the spin pointing like this. After 1 period, I came back to a state that pointed that way, but it has this funny minus sign associated. And if I do this one more time, this time again it's pointing along that direction, but that minus has become plus. Which means that after 2 rotations, you came back to identically the same state you started with. After 1, you came back to something that was very close, but not quite. It had that minus sign. You might say, okay, look, the minus sign won't typically matter. If I look at any probabilities, that minus sign is just a phase factor. It's going to disappear. So for all intents and purposes, that minus sign is just a trivial thing. But the appearance of that minus sign, I just want to point out very quickly, is because of a particular reason. Does anyone know what the reason is? Yes?
I know sort of the reason given, like, only without the math would be that these are not rotating in SO3. So in space that they are rotating, you need 720 degrees to get a full, to get back to it.
Not 360. Or if I'm doing it on a plane, that not that 360 but 720.
Yeah, like that. Yeah.
So he used words like SO3 and stuff. Okay, so if you don't know what this means, it basically means that imagine that you have a vector in 3-dimensional space and you fix the length of that vector, you normalized it such that it's 1. So then all the rotations of this vector on the surface of that sphere, okay, you know that if you rotate about any plane by 360 degrees, you should come back to yourself. There should be nothing special. No minus sign should accrue. It turns out that for spin half, the group of rotations, so there's this mathematical subject called group theory, where you study things like these rotations in great detail. Okay. Now it turns out that the group of rotations that governs spin half is not exactly this SO3. It's a related group called SU2, and that's got a twist in it. Okay. It turns out that this difference is what leads to the fact that if you come back after 1 rotation, you haven't come back to yourself. You come back to yourself but with a minus sign. But if you do twice, then you come back to yourself. Okay. Mathematicians give it some very beautiful names like the double covering of this group brings you back to yourself, etc., etc. You will learn all of this in a course in group theory later. Or maybe if in the mathematical physics course they do enough on groups, you might see it there. I'm not really a luxury to get into the mathematical niceties of that, but that minus sign is essentially coming from that group theoretic structure. Another way to see this actually is this rather beautiful demonstration. So, anyone in this audience know Bharatanatyam? Anyone? There might be somebody here. Yes, wonderful. So, what I'm going to do is probably going to look familiar to you. This is actually a dance move. I'm not a good dancer, but I know how to do this particular move. Turns out that there is a move in Bharatanatyam where the person holds a thali on their hand, and it's got diyas on it. Okay? Alright? And then they do this. Note. They're taking this thali all the way around, and they come back and note, if you were just staring at my palm, you would say, yeah, the palm is again pointing at you. But not quite. My shoulder is screwed up. Badly screwed up actually. To get it straight again, I need to do this. And now it's come back. But note, 360 degrees, but the twist in my arm is that minus sign. So I do one more twist, 720, it's come back to itself. You might think of this as a cheap trick, it's not. It turns out that the reason that minus sign is coming about is essentially identical to the problem with my shoulder. There's a constraint. My shoulder is not able to unhinge itself such that when I do this, I come back directly. I have to do it twice. Okay? It's a peculiar thing. Okay? There are all kinds of fancy names that go with this. Berry phases, Hannay angles, all kinds of stuff. Okay? You will explore more of this as you go ahead. Alright? But it's peculiar. And in spin half, that minus sign is essentially this thing. You may have seen this move, right? It probably never occurred to you that that's very funny, right? But it turns out that there's deep maths behind why your shoulder constrains you to come back. Okay.
What is the consequence?
The constraint here, the constraint there, it has to do with the group theoretic structure. I don't really want to get into that. You have to do the maths and then you'll see the constraint. The constraint is pretty much the same as the fact that Sx square plus Sy square plus Sz square is equal to S square. You fix the length, okay, and the determinant has to be equal to -1. That's SU2 group. Okay, 2 generators, determinant -1, traceless, matrices, the generators are all traceless. All those constraints actually lead to this. There are lots of physical significance. I won't get into it here. But there are lots of things. But there is one physical significance that I'll show you, not for this thing, but for what we're discussing here. So this was a nice aside. The fact that the spin does come back to itself with a minus sign, and if you do it twice, it comes back really to itself. Okay, fine, okay. But let's continue this game. So this guy, so far what have we seen? If I go in a full period, I come back to myself, except for this minus sign, which is not really terribly important for this discussion. But I do. But then you could say, but wait, Siddhartha, what happened in the middle? You're only telling me what happened after one full period. During this motion, what happened? Potentially, this guy is pointing on the surface of a sphere, right? That's clear. So, did it actually do this circuit on the plane? Or did the spin actually go up like that, do something weird, and then come back after one full period? Who knows? This is quantum mechanics, right? Our classical intuition is short. It could have been doing something completely bizarre. It could have sort of wandered all around for one happy period and then turns up exactly pointing where it was supposed to. I mean, there are Heisenberg uncertainties at play in this business. Okay? So it's not clear. So let's check. So what's the way to check? Well, let's look at what happens after a quarter time period. Let's do the mundane, boring thing. Let's make measurements of this spin's position after certain fixed times. So let's check after a quarter period, a half period, 3/4 period. Is it pointing the way my classical intuition tells me? That way, at least I can narrow down what's happening. So the way to do this is, okay, let's take the half time period. We saw 2 pi by omega comes back to itself. What about pi by omega? Okay, pi by omega, you feed that the time factor in, and it turns out that you get up to a phase factor of e to the I pi by 2, you get the spin pointing left. So, started like this, pointing right, after half period, up to a phase, it's pointing left. Now, if you allow me to say that, look, in probabilities, if I compute probabilities now, this phase is not going to matter. So, therefore, I have actually undergone a half rotation. Not bad. So, that means that my classical intuition is working out. But what if in going from here to here, again, this thing wandered off and then somehow again comes back to here after half period. So let's constrain this a little further. Let's look at a quarter period. Okay. So if you do it at a quarter period, okay, that's pi by 2 omega. You see that indeed now the spin is pointing in the y, plus y direction with the phase. So that is plus x. It's now pointing at plus y after one point. And we've also confirmed that after half it's pointing along minus x. So now, if you were a betting person, like we were discussing in the beginning of this thing, how many of you would bet against the fact that at 3/4 the spin is going to be pointing along minus y? I doubt any of you would. Yes, Aranya, you would bet against this? Okay, let's do the maths. Turns out you're going to lose. It is pointing along the minus y direction with the phase. Okay, so indeed we can see that that's what's happening. Time 0, x. Time 1/4 of the period, y. half period minus x, 3/4 period minus y, and full period back to x. There are these quantum mechanical phases that are in the game. Okay, probabilities won't see these phases. All right. So as far as the spin rotation is concerned, that's happening. That's what we call spin precession. Okay. So a small aside, what have we seen here? I have a magnetic field along the x-axis, along the z-axis. I keep a spin along on the xy plane. It starts rotating. I took a specific example where I made the spin point along the x direction, and then I started this game and I showed it to you. In principle, if you would have started the spin along the y direction or any other direction in the xy plane, it would have done this precession. It's guaranteed. The maths might be a little more complicated, but this is what we'll obtain. Okay. Now it turns out that you might think, great. So what's the big deal? I mean, classically I knew this was going to happen. My goodness, if you would have reached that conclusion, you actually would have swept aside one of the most exciting discoveries that came about in the 20th century thanks to quantum mechanics. It's called nuclear magnetic resonance, NMR. It won not one but 2 Nobel Prizes, and for very good reason. Because it turns out that NMR is one of those methods that people have learned to probe different kinds of systems with, whether they're in liquid state or solid state, whether those are physics problems, or biological problems, proteins and DNA. They also probe those things with NMR. So that's state-of-the-art way of actually doing things in biology as well. And it turns out that we all know what NMR actually is, at least intuitively. Some of us have even been unfortunate enough to tear a muscle and end up in a hospital under an MRI scanner. MRI is magnetic resonance imaging. It uses nuclear magnetic resonance, which is basically this physics. What they do is that, remember, we are made out of how much percent water? 70%? That's a lot of water if you think about it. Okay. Now it turns out water has H2O, right? And each of these H's, right, has given one electron across to the oxygen. So each of these H's has its proton inside the nucleus. The electron is kind of wandered off to the oxygen. So this proton, has a spin associated with it. And what they do in NMR is that they actually place the human sample, if you wish. That cricketer who tore his, some muscle or something, and poor guy had to be taken to the hospital. What they did was they stuck him inside the MRI machine, and you have to be very still when you do this, by the way. It's pretty, feels a little scary. It's not as if you die or anything, but they tell you to be absolutely still. And then you're just lying there. And then what they do is they subject you to a pretty strong magnetic field. Does anyone know how strong a typical magnetic field in an MRI machine can get?
10 Tesla.
Yeah, it's of the order of a few Tesla actually. So this might not sound very strong to you. It's just Tesla, right? But if some of you attended my classes back in the first year, you remember I impressed on you that a single Tesla is a shitload of magnetic field. Why? Because if you look at the Earth's magnetic field, that's really weak. That's 1/10,000th of a Tesla, right? That's really small. So 7 Tesla, in something like 7 Tesla, it's huge. That's why they tell you, please take off all your metallic ornaments. If you're wearing necklaces, rings, take everything off. Because you know what's going to happen, right? Your metals, magnetic fields, currents start running around here and there, things start heating up. It's crazy. So anyway, you're lying there, and what are they doing to you? They're actually using the strong magnetic field pulse. They send the magnetic field pulse, and they direct it at that where that torn muscle is, and the water molecules in the neighborhood of that torn muscle are going to do some funny business. They will start precessing. And then they switch off the magnetic field, and this precession relaxes. The protons again get confused. It is from that process of exciting this, causing the proton to precess, and then watching it relax after you switched off the magnetic field. That's what MRI imaging is all about, it turns out. So people have made an art out of this now. So that's why nuclear magnetic resonance has turned out to be so important through its applications in various branches of science. In fact, we have NMR machines on campus, and those NMR machines are always in use. You know, whether it's the chemist, biologist, physicist, everyone wants to send their sample to the NMR machine to get it checked out. Okay, whether it's solid, liquid, whatever. All right. So, yeah, so that's just basically this. So next time somebody throws NMR at you, you tell them, yeah, it's basically spin precession in the magnetic field, right? Almost there. Okay. All right. Okay. Yeah.
So, from this spin, I have one question.
Yeah.
So, we see hydrogen of 21 centimeter line.
Oh.
It's due to this spin. Why does the spin then anti-parallel, like align?
Yeah, I'll come and talk about that later. That 21 centimeter line thing will actually turn up somewhere later down in this course. So I will not be able to answer this question at this point. Nice question. But you will see glimpses of all of this coming as we go along. So remember, your question was, why does the spin actually anti-align? But think about the word anti-align. Anti-align with what? A magnetic field or something else?
Electron,
So whose spin anti-aligns with whom?
proton and electron.
So the proton and electrons, according to you, spins anti-align. But just ask yourself, how can such a thing even happen if these guys are not even talking to one another? So then the answer is clear. They must be interacting with one another at some level. But did you actually encounter this when you solved the hydrogen atom problem? Did your instructor write down for you in the Hamiltonian, along with that Coulomb potential? Did he or she actually also tell you that, look, there's a spin for the electron, there's a spin for the proton, and these two guys must be talking to one another? We do it in this course, to some extent. So we'll come to some of that as we go ahead. We'll unpeel this.
Sir,
Yeah.
you have written minus for 3 quarters.
Ah.
So how is that this minus 5? Because that will be minus 1 anyway.
Look at the state.
Yeah, that will
The state that's coming out is basically the other guy. It's not plus y. This is minus y. This other guy is plus y. Along the y-axis, this fellow is what? It was defined as the plus y guy. Remember? If we go up, let's look at, we wrote this somewhere. Oh boy. Yeah, here. Look at these guys. We define them. Yeah. So, true.
So when we have a magnetic field that is aligned along the z-axis, it shouldn't change the spin which is along the z. But how is it changing the linear combination?
No, that's because, for starters, remember in this thought experiment, we had the spin initially along the x direction, in the xy plane. So it keeps it rotating along the xy plane.
No, I'm talking about today what we are doing, the precession thing. So when the magnetic field is along the z,
Yes.
the z spin is not change.
If the spin is if it's initially aligned along z, but if it's not,
So for the state x, it is a superposition of your z, right?
no, wait. If the spin is initially along z, it won't precess. Second case, spin is along x. Now what will it do?
But it's superposition of your 2 of the z, right?
True,
That's
true, true. But the time evolution still causes it to precess, which means that basically the linear combination of up and down is also evolving. They're individually evolving in such a way that plus x goes to minus x after half a time period.
But when it was just z, it was not evolving.
If it's just said, then it's not evolving because this guy is completely aligned. Now, if you haven't guessed, so another way of asking the question you are is, what is the equation of motion for the spin vector in the presence of such a field, right? So what I showed you is how the states evolve. We can also ask the question, the way in the classical mechanics course you would ask it. What is the equation of motion for the spin? Right? ddt of s vector. You could ask that question. Let's do that next. But are you convinced that my demonstration shows to you that the spin is processing? Yeah. Yes.
So you check the definition that it was 1 minus I.
And 1 plus I.
So in this one you minus 1 I is
So this phase factor has also come out, right?
So the whole resultant will be in the up to this phase factor. Then written,
Yes. Sure.
So the whole resultant reaction will be in the
So there will be phase factor and then there will be that state. Yeah, so are you worrying about the phase factor?
I was just confusing about how the phase factor was coming. If I do the exact calculation,
It will come. Do the maths. Yeah. You have to be careful, you have to do the bookkeeping carefully. That's all. But no. Look at this, the way things are coming out here. I managed to actually factor out a 1i here, okay? And here it's a minus 1i. I can take the minus 1 outside, it will be 1 minus I. That doesn't matter. That minus 1 that comes out will be an additional factor e to the I pi. Right? But the important phase factor here is this guy. This 1 minus I and this 1 plus I. This is the important thing. Right? Okay. So now, let's ask ourselves, so we saw things as a Schrodinger evolution, if you wish. We started with a state, we allowed the state to evolve, and we saw that indeed the state is precession. But let's look at it from the Heisenberg picture. Since we know how to do these things now, let's ask ourselves the same question, but from the Heisenberg approach. If we allowed the spin operator to evolve in time, if we took that approach, how would this happen? Okay, you can do that as well. Now remember, the Hamiltonian is just a Zeeman Hamiltonian. It is this S vector dot B with some prefactors that give everything finally the dimensions of energy. Okay, so there's a Landé factor, G sub S. There's the Bohr magneton divided by H bar, and there's a minus sign. What does the minus sign tell us? Let's see how awake you guys feel. There's a minus sign in that Hamiltonian. What is that minus sign indicating? You might think that's just a detailing, big deal. No, wait. It's telling you some physics. Even a minus sign can tell you physics. What's it telling you? Come on, guys. Surely you know by now how to read an equation. It's telling you something very simple, that if S aligns with the magnetic field, you save energy, you lower the energy. Yes or no? Yeah? Stability. The magnetic field is telling the spin, align with me, we'll go into a happy state. Come on. You guys asleep or what? Let's give the simplest physics question on earth. That minus sign. If it were plus, what would it tell you? It would cost you if you were aligning with the magnetic field. Would that be a happy state? No way. Then you'd want to stay opposite to the magnetic field. Right? But we know that the magnetic field actually wants the spin to align with it. So the minus sign is important. Okay. So, Heisenberg equations of motion. We all know how this works. If you have the time evolution of the S operator, then that is just I by H bar, commutator of the Hamiltonian with the spin operator. And the Hamiltonian has spin in it. So obviously there's going to be something non-trivial because the Hamiltonian has spin in it, and I want to know the spin's evolution. So this guy is basically S dot V, that object, and its commutator with S itself. Now you'd be very foolish to think that this is exactly zero. Unless you've done the algebra, it'll be hard for you to convince yourself that this commutator must be zero. If it turns out that this commutator is equal to zero, what does that mean? That the spin operator will never change. But then how would you ever see spin precession from this? We saw that the state does change. So that's another way in which you can convince yourself that this commutator can never be zero. Right? Unless something very special happens. We'll see what that is. Okay. So how do you actually evaluate something like this? Be smart. Do it component-wise. Right? And then if you're feeling lazy, generalize. But let's at least do the first component. Okay? Let's do Sx. So that is, from S dot V, I take Sx Vx, just that term. Okay? And from the S vector, I've just kept Sy and Sz. Why didn't I keep the full S vector? Because the Sx part will commute with this. So I didn't bother writing it down. So now you can see that these are the only two terms that can be non-zero. Why? Because Sx and Sy don't commute, Sx and Sz don't commute. So therefore these two terms have to be non-zero. Now individually they're non-zero. You might say, but by some conspiracy maybe they'll cancel each other out, right? But that will take a miracle actually. So let's look at the first guy. We have Sx dx with Sy along j cap. Okay, but now note the bx commutes with everything, so that guy just sits outside, and it's just Sx with Sy. Sx with Sy generates Sz according to the Sx, Sy, Sz triad. Okay, so this just generates I h bar Sz. Okay, along j cap. And the other fellow is Sx with Sz, but Sx with Sz I'm actually going against the circle. So which means that this will generate a minus sign, okay, minus I h bar Sy. Okay. So then do all the maths and you see that this simplifies to something that looks like this. Sy bx along j cap minus Sy b. Sorry, did I get this right? So this is Sz bx. This should be Sz bx. This is Sz bx along j cap minus Sy bx along j cap. Okay. Now, even if I didn't tell you everything after this, by just looking at this, are you intelligent enough to tell me what this equation will look like? Let's look at that first term. Isi ko dekho. Look at that first guy and tell me what this will generalize to. You have Z coming with X, Z of the spin vector with X of the magnetic field vector, and Y of the spin vector with X of this guy. And note the directions are also all different. Huh? Z with X goes along J cap, Y with X goes along K cap. So क्या हो रहा है यहाँ पे? What is this? Come on guys, you don't need to be in Landau's school in Russia to figure out this one. No? Very good. Now can you tell me in more mundane first year physics level course what this guy looks like? Yes, it's the cross product guys. What else can it be? Okay. So you do the other two terms and it turns out that the other two guys all beautifully fit into something that looks like a cross product. Fit everything in, okay, so take these three components from all these guys, okay, and you indeed see that a beautiful S cross B turns up. That's what this guy looks like, okay, so this is called the Landau-Lifshitz equation of motion for spin torque. Spin precession is also called spin torque, okay, and does the word torque actually make sense now? If you think back to what you learned about torque, torque was what? A vector product, right? Of what with what? Force with? Of the displacement, right? From the pivot, right? No, we are getting something similar. It's not exactly one-to-one, that can't be, but you have a cross product again. So that's why when Landau and Lifshitz came up with this, okay, in order to explain some experiments, they immediately said, oh my goodness, this is just torque. The magnetic field is exerting a torque on the magnetic moment. It's causing it to precess. All precessions are associated with torque. What else? Good. And the nice thing is that if you look at this carefully, you see that the Lambda frequency is hidden. Wow. Noisy. So if you can see, if you look at the equation of motion, you'll see that the Lambda frequency is hidden in there. How is it hidden in there? Lambda frequency is EB by M. The E by M factor is automatically there. The V is just coming from the modulus of the B vector. Okay, that's it. So now, when is this spin evolution going to be trivial, guys? Huh? When S and B are aligned. Or anti-parallel. Which is almost the same. Okay, but when they're parallel, let's take the case of parallel. When B was along the Z direction, S was along the Z direction, what happened there? There was no precession. ddt of S was 0. That's right. The spin won't move, its state is fixed. And when it's in the x direction, now you can see why that thing was happening. Because Z was the magnetic field was along the z direction, the spin was along the x direction initially. So then this cross product is the most it can be. It's the strongest. Why? Because these two vectors are exactly 90 degrees, this apart from one another. So this guy's going to be beautifully precise.
How do you determine GS? Is it determined experimentally or theoretically?
No, so good. Nice question. So GS equals to 2 turns up from the Dirac equation directly. It comes out of the the arguments that lead to the Dirac equation. This is the spin. This is telling you that the spin space is is different. This value of GS. That's another way of putting it. But it turns out that this GS value. So the answer to your short answer to the question is yes and no. Yes, it can be got theoretically, and no, there are things that also are obtained experimentally. The theory can't give you everything. So it turns out that there are corrections that were learned experimentally. Those corrections were then also explained theoretically using quantum electrodynamics. Okay, so the simplest level of the Dirac theory, an electron that is moving at close to the speed of light, its state space has this Landau factor 2, exactly 2. Not 2.000001, no, 2. But it turns out that as this electron is moving through close to the speed of light, it can actually emit photons and absorb photons all the time. It's actually happening all the time. Okay, it's never alone. It's always surrounded by a cloud of photons. And it needed the genius of people like Feynman, Schwinger, and Tomonaga to actually figure out how this cloud of photons is always talking to this electron as it moves. Okay? And by the time they figured that out, people like them did the calculations and showed that GS is not exactly 2. It's got a very, 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 very tiny correction to it. Okay? Coming from all this talking of light with matter. Nice question. Very nice question. Okay. So the last thing for today is a kind of it's a sanity check. It's a question that one of you had actually asked the other day, and I'd said, hold your horses, we'll come back to this. It's this following fact that, look, I've been repeating all the time, that spin has nothing to do with rotations in real space. Even though I kept using my, my stylus to keep moving right and left, or clockwise and anti-clockwise, these are just cartoons, okay, to explain, to help you visualize something. But you have to be careful that the spin space can't be visualized like you would do for orbital angular momentum. Orbital angular momentum of the electron in its orbital, S-wave orbital around the nucleus literally is that it's going around. Okay? Just like the Earth is going around the Sun, we are revolving, that electron is also going around the nucleus. There are subtleties because this is quantum mechanics. There are probabilities associated with where the electron can be, right? And subtleties of that kind. Things are not deterministic. So that's why we call those orbitals the cloud. It's a probability cloud. Okay? But the spin space is fundamentally different. and I've been saying this all the time. So then this led to the question that when I write down the full states for some electron, how should I write this down? Should I just write it down the way my instructor showed me in the hydrogen atom solution, which is that there'd be a R part, there'd be a theta part, there'd be a phi part? Do I just write those guys down and that's it? What about the spin? Did any one of you ask the instructor from the first course, how do we put in the spin information into the wave function? Did any of you ask that? Raise your hand if you did. You see, that's the magic of the first course. That in that first course, you're so tired by the time we solve that ugly, horrible, long thing, that you don't even bother to ask that question. You just see it, you heave a sigh of relief, oh my god, it's done, thank you, let's move on. And all they tell you about spin is that a factor of 2 will appear in a degeneracy somewhere. That's it. Or they'll go a little further and say, in each orbital, in each one of those states, I could have had an upspin electron, I could also have had a downspin electron. And they leave it at that. Okay? But you should have actually asked, you showed us how to write down the wave function for the electron. Now you're also telling us that there's an additional piece of information called spin. Then how do we write down this spin? So let's answer that question. So, if we are assuming that this spin degree of freedom doesn't talk to the orbital degree of freedom, okay? Let's say that there is no conversation between them. Then it turns out that you can show, this is easy, that the spin operator will commute to the position operator, it will commute to the momentum operator, God help you, it will commute even with the orbital angular momentum operator. Okay? And if that is the case, right, in that special circumstance, you can actually construct the complete wave function for the electron by just tagging onto it all the spin states. And it's done as follows. You can write down, okay, the total state, alright, as some position dependent piece. That's what we used to call the wave function. Then it will come with a ket, which will be your r theta phi. And then there will be the spin guy as well, up. Or there could also be another fellow. There could be similar guy, but with another different coefficient, let's call it psi minus. And that will come with the spin being in the down. Okay? So look at this guy, alright? So what have we done there? What we've done is that for each and every one of these components, I've taken the ket space for the real part, the real space part, and I've just tagged on to it in a direct product form. I've just tagged on the spin guy, the information from the spin space. What is that information? Either the spin could be up, or it could be down. So each component, this for instance, this piece, this is just a direct product. Okay? Look at the other piece, that's also direct product. But now look at this entire thing together. What does that look like to you? Can you now separate out the spin part and the spatial part from that guy? Can you? If I give you this linear superposition with these two direct product pieces, can you now filter out the spatial part and the spin part? Can you write psi? So my claim is, can you write psi as some grand r vector and times some grand spin vector with some number in front maybe? Can you write it this way? What do you think? All your fence sitters, either yes or no. Anybody who gives me the the first person to give me a correct answer gets a chocolate. Were you asking which one? Seriously, this is not negotiable? Okay, the cheapest one. In which case, you continue sitting on the fence. Oh, come on. Somebody tell me. Can you?
Yes.
Sure? Yeah? Sure, why not? Oh, come on, just look at that thing. Does it look like it's separable? No, it's not. That's obvious, guys. Sorry, I cheated about the chocolate. No. Come to my office. I'll keep the chocolates for you after. But you can't. And what this means that you can't is that the spin space is somehow weirdly intermingled with the spatial space in the total wave function. Does anyone know what this thing goes by a name, this intermingling? That's right, you've been watching YouTube, right? No? No? Okay. But this is what is called entanglement. When you take these wave functions of this kind, what do I mean by this kind? A linear superposition of many direct products, which cannot be written as just a single direct product. If you cannot write a wave function as a single direct product, then there is something special about that wave function. Okay? This object is known as a tensor product. Okay? We are stitching together different state spaces, okay, the spin space and the real space in such a way that we are getting an entangled state of matter. Okay, so that's how the state would look like. And what would the Hamiltonian look like for such a state? Well, you'd have the kinetic energy part, you'd have the Coulomb potential, you have to have that. But what about the orbital angular momentum, etc.? Well, if you remember, so this was the nice cheat that you allowed your instructor in the first course to get away with. You would remember that you never asked them the question, but sir or ma'am, if I were to put this object inside a magnetic field, what would happen? The hydrogen atom. Because that would have meant that the neat Hamiltonian that they had would have also had to come up with one extra piece. And then they would have had to tell you a lot more about spin. So the beautiful cheat was that they assumed the simplest problem on earth, that you just have the hydrogen atom sitting there in isolation, it feels no magnetic field, no electric field, nothing. That one is the one you solve. Okay, no matter how horrible it looked, that's all you solve. Okay. Now it turns out that in this course we're also going to do more interesting things with that hydrogen atom. It turns out that, like somebody like Hatin pointed out there, the spin of the electron actually is talking to the spin of the nucleus, of the proton inside the nucleus. Weakly, extremely weakly, but it is. So because of that, certain degeneracies are going to get lifted. You know, all those marvelous degeneracies you saw in the hydrogen atom spectrum, all of those are going to get lifted. Gradually, bit by bit by bit. Okay? You just have to look closely. Yes, we're going to see that too. It's called LS coupling.
In this N plus S, like,
Yes. Here they're not talking to one.
Right, here they're not. But what I understood was if there's a border space, then S is only essentially an operator on the spin.
Yes.
So like on R it does nothing.
No.
So similarly L on the spin should do nothing.
That's right. So even within that, in 19.62, that is still true. If you were to take that wave function and act with the spin on it, it can only act on the up or the down ones.
So the operators are still separate. You're saying
Right now, because L and S are not talking to one another.
but if they do, then they don't.
Then you remember that where we started this entire discussion from. L and S are no longer going to be good. It's going to be L plus S, J. That will be the good guy.
But it acts on the tensor space.
Now it will act on the entire tensor space, right? Okay. So as long as we don't have any conversations between the S operator and the L operator, again, that was what your instructor in the first course was doing. It turns out that that LS coupling is also actually there. Okay, so it turns out that atomic physics, which was an extremely important, thing, even in the early days of quantum mechanics, it remains very important today. But a lot of experiments in atomic physics are what led to the discovery of quantum mechanics, and those happened over several generations. And as experiments got more and more sophisticated, people began to understand that a lot of the assumptions that they've made, like L and S, don't talk to one another, not quite true. And there were many of these not quite truths as we go along. Okay, but we'll come to them slowly. Okay, any final questions for today? All right. If there aren't, then tomorrow we'll start on the next thing in the syllabus, which is stop worrying about the world of one angular momentum. Let's get to the world of two angular momenta. Hooray! Okay. From one we'll go to two, and we'll see what we can do with two.